Well, let's look at magnetostatics in matter, if you don't have any other questions. So we had already discussed electrostatics in matter. Now it's magnetostatics in matter, how things will change. Now for this derivation, you see in electrostatics, I follow the derivation from Jackson, which is formally more correct. It's a bit more tedious, but formally more correct. The derivation in the book was not, strictly speaking, correct. The result was correct. Now for in magnetostatics, I will basically follow the derivation in the book, just keeping in mind that there are certain steps in the derivation which is not, strictly speaking, correct, but they give you the same correct result, and the strictly speaking correct derivation doesn't really tell much. We said that basically to calculate the magnetic field, we need to calculate the B field, the A field, the vector potential, and the vector potential for a general current density was, what was the current as an integral? It is J R prime. This is the A at the point R prime. There is a 1 over C R minus R prime D cubed R prime. Now if you consider a matter, we basically have two kinds of, we can just distinguish two kinds of currents. The currents that we actually put there, if you just take some metal, for example, a conductor, you can send a current there. But as we are sending a current through your material, we are actually sending charges. Those charges will also change the properties of the already existing charges. So that is, if you remember in electrostatics, we just separated two different kinds of charges. One, the charges that we actually put, that we call the free charges, plus the charges that were already existing in your system. So once we put some free charges, they modify the distribution of the existing charges, and hence creating an additional electric field due to this modification of the existing charges. So the total electric field was just the sum of the two. Now in the case of the currents, basically it's the same thing. So we have all these charges inside in a material bound to atoms. The charges are constantly moving around, the electrons are constantly moving, the nuclei are constantly vibrating. There is a local current running in our system. Once you send your current, an additional current in the system, it will modify the existing current. So you will get an additional contribution to the vector potential. So the vector potential we can basically separate into two parts. One part due to the free current density plus another part due to the, let's say, molecular current density. And this molecular current density, I mean, we can just basically make a multiple expansion of this molecular current density, and we have seen that we can actually write it in the form R minus R prime D cubed R prime plus, let's say, sum over the molecules. Let's say this is at the location Ri cross R minus Ri divided by R minus Ri cube. The second sum is the magnetic dipole moment, is a sum over all the atoms, in all the molecules in my system. So if I send the current in my system, it will modify the dipole moments of existing in my system. We will see how that modification will arise. One of the modifications is basically, we have seen that if you have a system which already has a magnetic dipole moment, it will try to rotate. There will be a torque acting on it. It will try to rotate its magnetic dipole moment in the direction of the B field that you have been applying, the external B field. So it will create a, on the average, even if you have a system made up of molecules having permanent magnetic dipole moments, they will be distributed randomly. So the net effect will be basically zero. But if you send some B field, if you apply an external B field, it will just align these magnetic dipoles in the direction of the external B field, and hence you will get a net magnetic dipole moment in a given region, which will create an additional B field. So that is the second term. And then we will define, I'm just skipping certain steps, we can convert this summation over all the atoms to an integration over the average magnetic dipole moment in a given region. And so we will write this as 1 over C JF R prime over R minus R prime D cubed R prime plus, well, it's not summation, it's now an integration of the magnetization at the point R prime cross R minus R prime over R minus R prime cube. Now this magnetization at the point R, we basically define it as the total molecular magnetic dipole moment. Ri is in delta V. So what we do is we just choose a volume delta V around this point R, and then obtain the total magnetic dipole moment within this delta V and divide by delta V. That's how we define this average magnetization. And just like in electrostatics, this averaging we will be doing over very small volumes, but nevertheless large compared to the molecular sizes, so that we can basically treat the system. We will be treating our system as homogeneous, not discrete. To be able to do that, we have to kind of average over volumes that are large compared to the molecular size, but nevertheless very small compared to the macroscopic size of our object. So this is the vector potential created in matter. Now, the part that is not strictly correct over here was, you see, this vector potential, this macroscopic vector potential, is also obtained by averaging over some volume. So these macroscopic fields in matter, we just average them over very small volumes, so that A is average over a small volume. Now this multipole expansion, strictly speaking, is correct if the molecules are not inside my volume, because that multipole expansion is valid if R is very far away from Ri. The point R and Ri, their separation should be much larger than the size of the molecule. That we can only be sure if Ri is out of my averaging volume. Inside this volume over which I'm averaging A, I have to do something else, but that something else, although it's complicating the derivation, it doesn't really change the final result. So I will stick with this approximation. But just keep in mind that there's such a subtlety in this derivation, a step that is not correct, strictly speaking. Okay, so this is our vector potential. Now, the next thing I would like to do is I would like to, again, if you remember our discussion on electrostatics, electric fields in matter, we basically had a similar expression. We had this monopole term. Instead of the current density, we had the charge density, and we also had a term similar to the second one. Due to the electric dipole moment of the molecules or the polarization of our system, and what we did was we wrote the second term as our first term and identified some effective current density. We said that, okay, if you take your system, put it in an electric field, it will polarize our system, and this polarization just behaves as some volume charge density plus some surface charge density. This is what we will do with the second term over here also. We would like to write it in a form similar to the first term, so that we will be able to model, in a sense, this magnetization of my system as a kind of some current density, volume current density, and some surface current density. So that's what we will be trying to do now. Now, to make that identification, let us start with it. But this is nothing but, well, let me just keep the integral as it is. Of 1 over r minus r prime. Well, this gradient is with respect to the primed coordinate. So if it was for the r coordinate, I should have put a minus sign. But since it is with respect to the primed coordinate, I don't need that minus sign. Well, let's also take the I component of this vector. Now, the I component of that vector will be epsilon I j k d cubed r prime mj prime, let me just call it mj prime. That primed over mj just means I'm evaluating it at the point r prime, times del over del xk of 1 over r minus r prime, or this is equal to epsilon I j k d cubed r prime del over del xk of mj prime 1 over r minus r prime minus 1 over r minus r prime del mj prime over del xk prime. The derivatives are with respect to the coordinates of the primed coordinate, primed position. Which will be equal to d cubed r prime. Well, this first term over here is just minus the curl of m prime times 1 over r minus r prime y minus, well, basically I have to exchange the order of j and k to be able to write it as a curl. So that is why I have that additional minus sign over there. And in the last one, again, I have to exchange the order, so the last one would be just plus the curl of m prime divided by r minus r prime, and the I component of this thing. So I obtain at least partially what I was looking for. This is equal to d cubed r prime. Let me take the minus out. The curl with respect to the primed coordinates of m prime over r minus r prime plus d cubed r prime curl of m prime divided by r minus r prime. Now, if you compare it with this expansion over here, you see the first term is j over c divided by r minus r prime integrated over. So this term over here is curl of m divided by r minus r prime. So basically the second term would correspond to some volume current density due to this magnetization of my system. That's the local bound current density. Now what I need to do is I need to convert the first integral to a surface integral. If it was the divergence, it would have been trivial. So what's your proposal? How can we convert? Can we convert d cubed r prime, the curl of any vector field, can we write it as some kind of a surface integral? So what we need to do is we have to convert this somehow to JB. Yeah, basically we need to convert this one m prime over r minus r prime to JB, surface integral of some JB. We have to identify what that JB is of r minus r prime. So let us see. Let us start with this one. Let us look at the I component of this one. This is equal to epsilon I jk d cubed r prime del over del xj of m prime k over r minus r prime. Well, this is the integral of the derivative. So we can just write it as epsilon I jk dsk of del over del xj sk is our area vector, the component of the area vector perpendicular to the k direction. Sorry, not the k direction, but the j direction. So, and I don't have that derivative. Sorry. This is dsj. So basically, let's see, if we are integrating over x, let's say that xj is x, so we should be taking I'm just considering the x integral of the derivative with respect to x. What I obtain is I just obtain the values of whatever that m is on the boundaries of x. But at the boundaries of x, I'm at the surface, at my surface. This is a surface in the three-dimensional case. And those surfaces, the area vectors, are in the x direction, perpendicular to my area. So I have the upper limit and the lower limit, but the upper and the lower limits are the parts of my surface, Sj. So that's basically what I'm doing over here. Did it make sense? Okay, let me do this simple example. Let me just take x, y, z. And let me assume a cube over here. Okay. And I have an integral over x, the integral over y, the integral over z. And then let me consider the df by some function df by dx. This is equal to dy dz times x goes from 0 to a. Then this is f at x is equal to a minus f at x is equal to 0. Of course, this f also depends on y and z. This is equal to dy dz f at x is equal to a y z minus dy dz f at x is equal to 0 of y and z. Now let me consider a very small patch over here, area. What is the area vector here? It's this one. So the s vector there is dy dz in the z-hat direction. In the x-hat direction, yes. So the x component of this ds vector is dy dz. I can take a patch over here. ds vector will be pointing in that direction. It will be, again, dy dz, but in the minus x direction. So dsx will be minus dy dz. So this will be equal to dsk, f of x is equal to a, y, and z, plus dsk, f x is equal to dsx, sorry. X is equal to 0, y, and z. Let me take a patch over here. This is the direction of ds, which will be dx dz in the y-hat direction. So dsx will be 0. Now let's see. This integral, the first term, is the surface integral over this surface. The second term is the surface integral over this surface. Well, the other surface integrals, if I take the x components, they will all be 0, so I can just add them. So this is nothing but equal to over all the surface of dsx times f. For all the surfaces, I am taking dsx. Well, the surface contains these sides also, but those sides don't. If I write the ds vector on those sides, it doesn't have an x component, so their contribution to this integral will be 0. So if I take a volume integral of a function, the derivative of a function with respect to x, the only thing I need to do is I can convert it to a surface integral, but I have to make sure that when I'm writing down the surface vector, I have to take the x component only. Now, in fact, this gives us our well-known result. Let's say dv, the divergence of any vector field. This is nothing but dv, the derivative with respect to xi of fi. But I said that if I have any function take its derivative with respect to xi, I can always convert it to a surface integral using only the I component of my area vector. Fi, but this is nothing but ds dot f. Now, this is the result that we are always using. Now, this result over here that I use, this one over here is the generalization, or this one that I claimed claimed in this derivation, this discussion, is kind of a generalization. It doesn't really have to be a divergence. It has to be some kind of a derivative. That's enough. If that is correct, well, let's come back over here. But this is nothing but ds vector cross product with m prime over r minus r prime, the I component. So this integral over here, d cubed r prime, times the curl of m prime over r minus r prime, magnitude. This is equal to the integral of ds cross m prime over r minus r prime. But this ds vector is in the normal direction, and let me write it as ds, the magnitude as ds. So this d cubed r prime, curl with respect to prime coordinates of m prime over r minus r prime, is equal to ds n cross m prime over r minus r prime. What does it? Well, it commutes. It's just some number, some vector. It multiplies everything. So this r minus r prime is just some kind of a number. I can take it out of the cross product. Since it's not a derivative, I don't really need to worry about it. You see, n cross m prime over r minus r prime is I have one vector taking the cross product with another vector divided by a number. I can take that number out. It's the same thing. Okay, so let's sum up. You see, we were writing this vector potential. There is one part from the free current running in my system. Then there is this second part. Okay, there is the second part due to the magnetization of my system. And that magnetization of my system, we said that, okay, there is one part of it, this part. They are to be separated into two parts. There is this one written as a volume integral. Plus there is another part which we wrote as a surface integral. This is, of course, the closed surface. It's the boundary of my volume. So basically, if you have this magnetized system, I can always treat this magnetized system as some kind of a bound charge density, bound current density running in my system, given by the curl of this magnetization, and also a surface current density, bound surface current density, given by n cross m. Well, to compare it with the case in electrostatics, if you remember in electrostatics, the bound charge density was nothing but the divergence of polarization. And the surface charge density was nothing but the normal component of polarization. Now we have the curl and the cross product with the normal direction. Well, let's see. These are multiplied by C. So the effects of the medium we can describe in terms of this bound volume current density and the bound surface current density. So in fact, we can just write down the modifications of our equations. The divergence of B, well, it doesn't depend on the current anyway, it's always 0. But curl of B, which was given by 1 over C times J. This is the total J. This is 1 over C times J. Let's call it free for the time being. Plus JB. We are writing it in the volume. The boundary, we have to treat it in some different way. So the curl of B will be equal to this current. And curl of B is equal to 1 over C JF plus curl of M. Well, there are many 4 pi's that I forgot. I think here there is a 4 pi. This 4 pi over C. So these should be C over 4 pi, C over 4 pi. Sorry. I made another mistake. No, okay. Yeah, we can treat it like this. I know the A, if you want, you can just from the A take the curl of A to get the B, and from that expression just take the curl of B and you will get this expression. But rather than taking the curl and the curl, we already know that curl of B should be equal to 4 pi over C times the current, which is the total current, and let me see, J is equal to C over 4 pi. Yeah, okay. There is a 4 pi missing. Well, the next thing I will do is curl of B minus M is equal to 4 pi over C times J free. This will be our H. This is the magnetic intensity, magnetic field. Okay, I was trying to always pay attention to always calling this B as our magnetic induction field. This H is the magnetic field. Now let's see, where did we forget this 4 pi's? Okay, so in the identification of J's, there are no 4 pi's. You see, in the expression for A, there are no 4 pi's. So J is just C times the curl of M. So here I get a 4 pi curl of M. So here I have a 4 pi times M, the magnetization. So now we have this new field, which we defined as B minus 4 pi times the magnetization of my system. And the curl of this H field is given by 4 pi over C times the free current running through my system. Well, if you make the analogy with the electrodynamics, electrostatics, well, there what we had done, well, we had this material, we put it in a medium. No, we have this material, we put it in an electric field. This electric field is either created by the charges we put in the system, or it can be an external electric field. It doesn't really matter. So whatever happens, whatever the origin is, you are creating an electric field which is created by the charges that are not already in my system. But this additional electric field modifies the charges in my system, and hence they will also start contributing to my electric field. Their charge density changes. So it will also contribute to my electric field. So electric field receives contributions from both the the charges that we put, and also due to the charges that are bound to the molecules in my material. And we say that this new electric field is due to the polarization of the medium. We define that this P field, the polarization field, and then using this P field, we obtain this displacement field, the D field, which was E plus 4 pi P. Now, D field was, if I'm not wrong, this was E minus 4 pi P or plus 4 pi P. I would say plus 4 pi P if I'm not wrong. Minus. So here this was minus. And we said that, okay, this polarization, we can also describe it as a kind of a bound charge density and the bound surface charge density. And we said that rho B was equal to the divergence of P. Now this is plus, this is minus. And sigma B was equal to n hat times P. Can somebody check the book? These two signs should be different. E plus P.
E plus P. No, with the coefficients. It's different in
D is equal E. This is plus.
Yes.
Yes. Oh. And now basically the same phenomena happens in the B and the B field. So you take your system, you either send some current density through your system, but you have some current density somewhere else, which we call the free current density, which creates a B field. This B field will change the currents in your material and creating a new kind of current inside an effective current inside your material due to the magnetic dipole moments of your system. And this new current will also contribute to the B field. So the B field, the total B field will receive contributions from both the current that you create and the current that is created inside your material. And you also define this new kind of field, H, which mainly depends, at least the equation that this new field satisfies depends only on J, on the current that you control. In the case of the D satisfied this equation. Divergence of D was equal to 4 pi rho. Now in this case, curl of H is 4 pi over C J. Now, what is this current? Let's just have a simple model of the atom, a simple material. Well, it's made up of atoms which have electrons. Electrons are rotating around. So let's just, for simplicity, let's assume that all of these electrons have a magnetic dipole moment in the same direction. So let's say you can just treat these electrons as small charged objects orbiting your loops. So you see, this is your nuclei. Around it, there is a current running in this direction. This is kind of our model. So this has a magnetic dipole moment out of the screen. Just next to it, there is another atom, another atom, another atom. Here, another one, another one, another one, etc. And all of them have their electrons orbiting in this direction, or have the currents running in this direction, the electrons orbiting in the opposite direction. Well, you see, if you look at, let's say, this point, at that point, there is one loop whose current is running in this direction. There is the other loop whose electron is orbiting the other, whose current is orbiting in the other direction. So the net current at that point would be 0 if the two atoms have the same dipole moment, magnetic dipole moment. So the net current at that point will be 0. So if the magnetization is uniform, all the atoms will more or less have the same magnetic dipole moment, and hence you won't get any current at that point. If magnetization is not uniform, which basically means that one atom has a different dipole moment than the other one, which can be, for example, one atom carries a larger current than the other one for some reason. In that case, at that point, you get a non-zero current, non-zero net current, although no charge is moving from any point to another point, but effectively, at that point, the currents do not cancel. So you obtain an effective current at that point, if magnetization is not uniform. So that is this curl of M, this JB, this bound current density, which is the curl of M. Actually, there is no current in the sense that no charge is moving from here to there. All the charges are local. But effectively at that point, some charges moving in this direction do not cancel the charges moving in the other direction. So that's why we obtain a current there. Now if you look at the surface, well, at this point there is a current running in this direction, at this point there is a current running in this direction, etc. So on the surface, effectively, there is a current running in this direction. This is our KB. You see, let's look at the direction of that current. This is my N, the normal direction to my surface. My magnetization is out of the screen. So apparently I have a sign mistake somewhere. N cross M. You see, this is N cross M is in this direction. Well, the current is basically in the opposite direction. KB is in the minus N cross M direction. So we have a sign problem somewhere. We don't have much time to go over to find the sign mistake. So basically this is why we have a surface current density corresponding to a given magnetization. Again, I repeat, there is no current in the sense that no charge is moving from this point to this point. All the charges are circling around their position, around the central position. But effectively, it acts as if there's a net current on the surface. At an intermediate point, all the currents cancel at that point because there is one current running in one direction, another current running in the other direction at a point inside my volume, if the magnetization is uniform. But even if the magnetization is uniform, there is no such cancellation on the surface. On the surface, there will always be some current, whose direction is given by the normal, determined by the normal vector and the M vector, the magnetization vector at that point. So let's go back. Let me see if we can find that sign mistake. So we had this expression, this di component epsilon ijk, derivative with respect to xj. Oh, that. Let's go back further. That minus sign, I forgot. Well, that minus sign over there, I mean, all this derivation is correct. Here I have a minus sign. So the bound charge density is minus C times N cross M. Okay, so everything now fits. Now, any questions? Well, on Friday, we basically will repeat what we had done before. We just said that the magnetization will be some constant times RB field, etc., and then we will define the magnetic susceptibility, magnetic permittivity, etc. So we basically will repeat what we had done in electrostatics. And next week, we will start the electrodynamics. Any questions? So see you on Friday. Just a reminder for you that in the exam, and if you also don't have any objection, I would rather do it on Sunday, not Saturday, on 25th. At 9:30? Hmm? 9:40 to 13. So even if you come at 2, at 10, you still will have 3 hours. Everything.
Electrodynamics.
No, probably not. I mean, I can still ask some simple questions on electrodynamics. Dynamics. That we will start next week, before the exam. Okay, so see you next Friday.